Hi, my name is Luis Montejo, and in this short video I'm going to show you how to use Reqpy. Reqpy is a module of Python functions that allow us to do spectral matching. Uh, so in the first example, we're going to do just a single component match. So the first thing will be to import from the Reqpy module the function that we'll be using. And in this case, Reqpy single, which is the function that allows us to do single component matching, and this other function that we're going to use to load the acceleration record. So you have to define the target spectrum. In this case will be a spectrum based on ASC7. You have to define the damping ratio, which is usually 5%, and you can also define the period range within which the spectral matching will be pursued. So in this case I'm gonna be matching between 0.05 seconds and 6 seconds. Okay, so here I'm loading the Cite record, and in here I'm calling Reqpy single to do the actual match, the actual spectral matching. So what do I need to specify to this function? I need to specify first the acceleration record, okay, the time history of acceleration, the sampling frequency for that time history. This is the spectral acceleration for the target spectrum, and these are the periods for those spectral accelerations. Then the limits for the matching, the period limits, the damping ratio, the number of iteration, which 15 is more than enough, and S is the number of scales to perform the continuous wavelet transform, and I will just leave it in 100. And baseline is, you can specify 1 or 0 depending on if you want the code to perform baseline correction or not. So I'm gonna leave the code to baseline correct the resulting record. And also for plots, if you specify 0, then it will not generate plots. I put 1, so it generates some plots for the results. And here it is just standard Python to save your results. So let's execute this. And when it is done, it's going to show you the root mean square error. In this case was 2.84%, and also the average misfit, that for this case was about 2%. Okay, the plots generate two plots. The first one is the comparison of the time histories for the scale seed record and the spectrally matched record, and the second one are the spectra. Okay, so here you have the spectrum for the seed record and also for the spectrally matched record. That will be the blue one, the dark blue one. Okay, that you see that it's going to match the target spectrum within the specified range. Remember that for this case was 0.05 seconds, here up to 6 seconds. Okay, so for this second example, I'm loading both of the horizontal components. Okay, and I'm making spectrally matching each of these components to the design spectrum just by calling Reqpy single as we did in the first example. So now we have this and these two horizontal components that have been spectrally matched, and I would like to see how the RotDnn for those components look. So I call this function RotDnn, which I imported here. Okay, and for this function I have to specify the two horizontal components, the time step, the damping ratio, and the periods at which I would like to generate the spectrum, and also the percentile. Okay, in this case I want RotDnn, so I specify 100. If you want the median spectra, well, you specify 50 here. So this function returns the actual RotDnn, in this case a RotDnn, and this will be a matrix with the response spectra at each of 180 different orientations. And here I'm just using matplotlib to plot the results. And so let's execute this. And the results are here. This gray area is actually 180 different response spectra, one for each of the 180 different orientations that were evaluated. So the envelope of all of these response spectra will be the RotDnn, which is denoted here by this dark red line. And you can see that the 110% requirement from ASC 7 for the spectral image record is at some point is substantially surpassed. Okay. Finally, in this last example, we are implementing what is proposed here in this article, which is basically using both horizontal components to pursue the match directly to the RotDnn target spectrum. So to accomplish that, we need to import this Reqpy RotDnn function. And just as for the previous example, we load both horizontal components from the Cite record. Okay. Now we use those two horizontal components S1 and S2 here to call the Reqpy RotDnn function. In addition, we need to specify the sampling frequency. This is the target spectrum and the periods at which that target spectrum is defined, and the percentile at which the target spectrum is defined. That for this example, it comes from ASC 7, so it's a RotD 100. So that's why I'm specifying here 100, but it could work also for a RotD 50, for example. We also specify the period range at which the matching will be pursued, the damping ratio, the number of iterations, the number of scales for the wavelet decomposition, and here I'm asking the code to also perform baseline correction and to generate some plots. Okay, so I'm going to execute this, and it will take some more time. It will take about 2 to 4 minutes depending on the length of the Cite record. So in this case, the root mean square error was just 1.9% and the average misfit 1.35%, which is quite good. If we go and see the plots that the function generated, it generates two different figures. One is the comparison for the time history. So now we have 6 plots because we have accelerations, velocity, and displacements for each of the horizontal components. And the other figure is showing the spectra. Okay. And we see that if we compare here the dark blue line, which is the resulting RotD 100 for this spectrally matched component, well, the match with the target spectrum is quite good. Okay, and if we compare this with the previous example, with the results from the previous example, we see that there is a big improvement on the match. Obviously, if our intention was to strictly comply with ASC 7 requirements, then we should have specified 110% design spectrum as our target spectrum to comply with this ASC 7 requirement for spectrally matched records. I think this is it for this video. I hope you find it useful, and I hope you find useful the codes provided. Bye.